stream? I promise people.
No, it's not, but we're just going to record and I'll upload it after.
Okay, yeah, that'll do too. Yeah, all right. Time I come here. Streaming.
Yeah, recording.
So I think we had few people inquired about being able to watch it online, but never mind, it should be fine. Well, if we can stream it, it should be fine. But anyway, all right. All right. Hello everyone. Welcome to the final research colloquium for the winter quarter today. Today we have Professor Alexander Rasin from DePaul University School of Computing and Digital Media. He's an associate professor and he received his PhD in computer science from the from Brown University. He's the co-director of Data Systems and Optimization Lab at CDM, and his research interests in the cybersecurity problems of preventing data tampering and exfiltration, establishing standards for database forensic analysis, and developing fine-grained access control policies. Dr. Rasin's other research projects focuses on building and tuning parameters of domain-specific data management systems, including biomedical data integration, user-defined predicate query optimization, and physical database design and indexing. So he has also received funding for his research from external funding agencies like NSF and NIST. So without further ado, I'd like to welcome Mr. Rasin to tell us more about his research in abstracting database memory to describe runtime operations.
Thank you very much for the introduction. So this is very much a new direction and extension of the follow-up to the work we've been doing. Therefore, there is going to be a lot of background and context to explain how this all fits and what we're trying to do with it. The idea is to understand what happens in memory or in RAM when you operate a database. And for that, there's quite a few applications at the C. The one use case that we've already dug into is understanding what happens with memory leaks and encryption. However, we see lots and lots of potential. This is very kind of early start. We just submitted the first draft to a conference, but this is brand new work on the cutting edge. So why are we trying to do this? Well, data is very valuable, as you know. It's the new oil or the new bacon, depending on who you talk to. And although I'm a little bit biased because I work with databases, but it is true that wherever you have valuable, secure, protected data on the back end of a website, on a personal device, there is a specialized SQLite database that's used in browsers and in personal devices, because when you store data, you don't want to reinvent the wheel, and therefore you use a database to keep track of whatever is it you have, whether it's a website backend or local storage on a device, or a number of very specialized applications like HR software, which is stored in PeopleSoft, owned by Oracle. And the bottom line, it's all stored in a database, and it's actually the database is a very separate black box environment that has a complete set of its own configuration, settings, and features. So if you think about an operating system, there is typically a mirror functionality for anything that an operating system does. So when you put data into a database, in an operating system you have caching, in database you have its own caching. In an operating system you have accounts and access permission, database has its own version within the system, and I use database or database management system interchangeably. I typically mean database management system, the software that runs the data control. Similarly, there is backup and logs and all sorts of components, as well as encryption, that will exist within the database management software that's completely independent and of the operating system. So for that reason, it merits a study, because there's just a separate world that is not really visible from the operating system level. So for a little bit of background, as a refresher of your intro to database course that you've taken, I'm going to talk about running queries and following where the data goes. And there are 4 types of queries that I might refer to. As a reminder, they're all using SQL, which is a standardized query language that lets you access data. The types of queries that I'll refer to are filter. That's simply going through the table and selecting rows based on a condition, such as finding all employees who are named Alice in this particular case. So this is the SQL equivalent for that. That's just scanning through the data. A more complicated query that, as you'll see, is referred to as memory-intensive operation might be sorting, which is, again, simple, where you just say select all employees sorted by salary. However, the reason why it is memory-intensive is because you have to construct a new set of data which you sort, rather than simply scan through the data already on disk. Similarly to that, you might do some sort of summary or aggregation. And this example is counting employees by city. So getting a total count for each city you have in your database. And once again, this constructs a new entity, a new data structure that will have this summary, which is independent of the original table. That's why it's known as memory-intensive operation. And finally, the last type of query that I will refer to is the join. A join lets you link together multiple tables. In this example, I have a set of employee records, a set of manager records, and they're connected by some sort of a key reference by ID, indicating which manager manages which employee. So a typical database consists of multiple tables that are connected by references and keys. And so continuing on to the background concepts, brief reminder, all of the database content is stored in pages. And this is similar to an operating system, and this page would often be matched to the operating system page, but it is something you configure for the database separately of the operating system. The page is an access unit, so when you access a disk, you have to read a page worth. That however many records it contains, or however many records you want from that page, you have to read the whole thing. Now, in order to actually look up data, you may need to use an index. Most databases utilize an index, typically something known as a B-tree index. There are multiple types of indexes, but the most popular one is known as a B-tree. It's simply a hierarchical tree structure, like the one in the picture, that does a divide and conquer lookup that lets you identify a specific record within a table. So the blue rectangles are the pages of the table, and the B-tree structure here is something that lets you look up a value. So let's say I was looking for an employee making 45,000. I would access the top page, then follow the pointer between 24 and 65, and come to the next level of the tree, and then follow the pointer corresponding to 45, which would send me to the actual data table, letting me find the page with the employee record. B-trees and almost every structure in the database is also stored in pages. So tables are chunked into pages of maybe 8 or 16 kilobytes, fixed size. And so are B-trees. They're also consisting of pages in the same way. They just serve an auxiliary function. Now, once you have those pages, there is a bit of a workflow process of how you might actually access and see those pages. So the data stored on disk, bottom left, we start from persistent storage, solid state or hard drive of any type. This is portraying a part of memory. So I am going to talk about RAM, obviously. Now RAM is a bigger thing. There's a chunk of memory that the operating system allocates to the database. What's portrayed here is specifically the I/O cache buffer, the component that keeps a copy of a page in memory to expedite access. So it's the same caching, it just happens within the database. Just like the operating system does it, except that databases do not trust the operating system to do caching and do their own. So for example, if the query accesses page 1 and page 2, I'm sorry, in this case, query modifies page 1 and page 2. The page is brought into memory, altered in memory, that's why it's page prime, page 1 prime, and page 2 prime. And it's kept there for some time until the memory is needed for some other purpose, at which point it's evicted. Again, it's the same caching process. It just happens within a database. So in this example, when query 2 reads page 4, you need to make some room. So you need to evict something. If the page is not modified, you can just throw it away. If it is modified, you have to write it back to disk so that the update actually reflects in storage, and then replace it in the I/O buffer cache. And you typically use some sort of LRU, less recently used policy, to do this move out. All right. So for a full picture, a little bit more backup. This is all relevant in terms of how data moves around in storage. So when you do access a table, you essentially have two options on how you might access its contents. So a table is a series of pages, and the two types of access you have are either full table scan, which is exactly what it sounds like. You read pages 1, 2, 3, 4, 5, and scan through the whole thing and pick out what you need. That's one way to execute a query. The other way to execute the query is an index lookup, where the index points you exactly where you need to go. In this case, I have an index pointing me to page 3, which saves me having to scan the whole table and lets me access the specific page instead. Now, one more structure that will also be relevant to what happens in memory is something called an index organized table. An index organized table is a hybrid construct that, instead of having an index and a table, it combines them into one hybrid entity. So instead of having an index that points to something that's a separate table structure, you essentially stuff the table into the index itself. So following my previous lookup of employees who make 45,000, I would read the root page of the index, and then I would go to the leaf page of the index, and instead of following another pointer to the table, I would find the data right there, which has certain advantages that do not come for free, but the big advantage is that that keeps the data organized and automatically, because indexes are self-organized to begin with. Does this, if anyone has any questions, by the way, feel free to ask. I know this is a lot of background, and I'll be referring back to it, but it is important to understand how data is accessed within the database system. All right. So, for even more background, a couple more terminology concepts that I will refer to when I talk about some of the results that we've collected. When you access the data, data goes into memory. There are rules about how things are cached. There are rules about how long the data stays in memory, and then eventually it will be written back to disk or freed up. Now, in general, when the database allocates a chunk of memory, it can be either global or local to the process that the database runs. So the database is a process within the operating system. It is more or less a black box to the operating system. There's just this big chunk of stuff that the database manages, just like we discussed. But when it does request memory from the operating system, that memory might be global, meaning available to the entire database process, or local, meaning created for a particular purpose. When the memory is local, it is created for whatever task I'm trying to do, and then released back into the wild, meaning given back to the operating system. And that, once again, is significant because when you release something you've allocated back to the operating system, it leaks, becoming available to whoever is the next one to allocate that memory. Anything that database keeps is more or less kept within the black box and not just released to the wilderness. Now, when you execute a table join, and this once again goes back to how the memory operation occurs. There's actually multiple types of a join, which is all part of query optimization and the decision on how to execute the query. For our purposes, the two significant types are either nested loop join or hash or merge are related. So intuitively, a nested loop join, and a join again is just where you match records from two different tables based on some condition. A nested loop join is a double for loop. You go through every page of one table, you go for every page of the other table in the inner for loop, and you match the records as you go. It is the naive version that is very expensive, and the reason it's different is because you're essentially reading through the table. It is not a memory-intensive operation. You don't have to build a new structure in the memory. You just have to read through the data you already have in the table. And therefore, it's expensive, but its upside is that it's always available, doesn't require any additional structure or cleverness. The more customized and more specialized joins are hash and merge, and there are others. They do something much more extensive. So for example, hash join builds a hash table and uses the hash table to perform the matching. A merge join sorts the tables and then performs a join assuming that the data is already sorted. All of those are more clever and more efficient, but they have a certain prerequisite. So a hash join requires you to construct the hash table. A merge join requires you to have sorted data or to sort it, which goes back to those are memory-intensive operations because you need a bunch more memory to make this happen. Where nested loop join, while expensive, is simply go through the data beginning to end. This will be referenced when we talk about what actually happens with memory when you run queries. Finally, I will refer to this transaction area or write-ahead log in a second. So a write-ahead log is an emergency disaster recovery contingency. So as databases run in some form, they make a note of every operation they perform in case the system crashes. Because when the system crashes, you come back up and you want to essentially see where you were, what you were doing, what you haven't finished doing, to be able to recover and resume operations. So write-ahead log or transaction log is this series of records of what have you been up to, so that you never caught off guard by a system failure or a crash. Now, given all of those pieces, we have identified, and we're finally starting to get into some actual results and experiments, and I'll be reminding you about all of the piles of terminology that we've gone through. On those bases, having looked at several major databases, and I have a list of things we've looked at, we've identified 4 types of memory that databases create. Now, as in this research and in our previous work, we try to keep this general. So those are not the only types of memory that a database may allocate, but those are common to every major relational database that we've looked at. In addition to that, there are specialized database-specific things that are a little bit less interesting because they only belong to this one database. So the 4 types, which by the way have radically different names and sometimes operate in a different fashion but serve the same purpose, are I/O buffer, which is the thing we've talked about. That's just the buffer that keeps copy of pages so that you don't have to go to disk. So you keep a copy in memory, cache it, and try to avoid having to access it. There is something called the sort area, or a memory-intensive area, which is for all operations that require additional RAM for processing. And that's why we made that distinction between different types of joins. The nested loop join lives in I/O buffer because it doesn't actually construct new structures. It just does the equivalent of a scan of a table. Merge and hash join and sorting operation, duplicate elimination, distinct aggregation would all live in the sort area because you create a new structure, so for that you request more memory. And then there are 2 other specialized but common types of memory. So transaction buffer, the write-ahead log thing, the emergency recovery thing, there is a memory for that. Every database has one where it keeps track of. And there is something called query cache, which keeps a few interesting things as well. So obviously it keeps the actual queries, like when you type in the SQL query, that's where it goes. But on top of that, it would also store something called query execution plan, which is essentially the decision of how to run the query. So when the query comes in, for example, you have to choose what kind of join to use. To go with hash join or nested loop join. That decision in aggregate is called the query execution plan. That would be cached in memory so that if a similar query shows up, the optimization can be reused. And also, a lot of databases allow SQL language extensions, PL SQL and Oracle, Transact SQL and Microsoft, general programming language tools that allow you to write functions or plug in C or Java code, the customized extension. So this custom code would also live in the query cache. All right, so that gives you a sense of the database operations and the important pieces of the database that we want to discuss. Now I want to talk a little bit, as our current primary use case that we've dug into is encryption. I want to talk a little bit about the encryption options. Now, before I talk about database encryption, I want to just mention the fact that there is something called client-side encryption. And everyone is pretty familiar with what encryption is. You take text, you convert it into ciphertext of some sort to make sure that no attacker can read your data. So client-side encryption actually means that you encrypt the data before you place it into a database. And that is in some sense simpler because you don't have to have the database support any encryption. You just store encrypted text to begin with. So instead of Alice, you might store this, which represents Alice, and database doesn't even know about it being encrypted. The problem with client-side encryption is that it limits your functionality because the database doesn't know. So for basic encryption, you can do range queries like salary greater than 50,000 because you don't have the numbers, you have ciphertext. For order-preserving encryption, which is a more specialized type of encryption invented to solve exactly that problem, you can do range queries, but you can do other functions like string pattern matching or some of the optimization options. And so there's a number of encryptions that were kind of repeatedly designed to make the functionality work, but A, they're all limited in some way, and B, you would have to choose the right type of encryption depending on what kind of queries you're going to run, and that's all a significant overhead, and ultimately you want the database to be aware and be working with you on supporting encryption, and that's why all of the database systems tend to have their own encryption within the system. And that's what I want to overview. Okay, so again, it's a very high level introduction to what is supported. It's far from standardized. We've reviewed that what options are available, and there's a table summary. But at a very high level, you can do two types of things in a database. You can do something we call instance level encryption, which means the whole database or the whole database file is encrypted by some key. And that further subdivides into, you can encrypt the whole thing and just provide the key, have the key stored in the database, and initialize and decrypt when you start. Right? And then you shut down the database or disconnect from a database, then everything goes back to being encrypted. When you connect, you establish the key that lets you read it. And a potential problem with the basic encryption is that you are trusting the database administrator to have access to it. So if the key is right there, then whoever manages the database can basically do what they want, read the data or even modify it. Therefore, the newer and more advanced take on the same thing is transparent data encryption that does compartmentalization of who can access the data. You still have the keys in the database that still encrypt the data, but you also have a master key that encrypts the in the database key so that the person running the database doesn't have complete access to what is happening. So in order to access the in database key, you have to have the master key, which is designed to live outside of the system and under someone else's control, not the person who manages the database. So bottom line, it's the same idea, but you take away some of the control from the person who supervises the database contents. So that's option one. Option two is something we call column level encryption. You could also think of it as value level encryption, where you encrypt the values in the database by calling encrypt-decrypt functions, essentially as you execute the query. So this is an example to give you a sense of how it might work. Let's say your name column is encrypted, and so instead of doing select name to fetch the names of the employees, you do select decrypt name and provide the key on execution. And so at that time, the decryption happens and you get back the actual value. So the obvious advantage is that you have much more granularity and control over it, because you could literally encrypt every value with a different key, or certainly every column. The downside is that your queries would actually carry the key around with them, and in addition to the fact that you have to supply one, this stuff also ends up landing in the query cache and memory, and that part would be open text because that's you saying decrypt and here's the key. There's also some specialized things that databases support. There are specialized client-side encryption that's built into the database. A couple of systems support that. And there's also masking, which is not quite encryption, but the process that, for example, zeroes out or X's out everything but the last 4 digits of social security number. That's what masking is. In terms of support, and to give you a sense of which databases we actually looked at, this is the databases and instance and column level encryption, and what do they actually support in terms of the encryption that's built into them. So most support some version, either basic or, so checkmark means basic, TT means transparent data encryption. And most of them support something, and it's implementation specific, and it's not super standard, but it is a similar functionality. That's sort of our go-to list of 8 databases that represent most of the relational database world. But it's actually more extensive because there are other systems that are not named here, like MariaDB is using the same engine as MySQL. Greenplum database, which is pretty big, is using the Postgres engine underneath. So there's a bunch of other systems that are basically some extensions from an open source offering that would follow the same rules. All right, so this is encryption, and now we finally get to look at some of the results that we've collected to try to see what actually happens with all of those pieces. So the reason we had to go through so much background is because there is a lot of database-specific terminology as to what happens when you run a database and access memory. So we have ran experiments on 3 representative databases out of this list of 8: Postgres, MySQL, and Oracle, that are both some of the more visible ones. And they're also curiously different in how they actually implement certain functionalities, so they are nicely representative of the type of things you see. And we use the star schema benchmark, which is a data warehousing benchmark with 5 tables that comes with a data generator and simulates industry standard data warehousing benchmark. And in order to track the memories within the process, we have designed a workload specifically for the purpose. Now, the different memory areas function a different way, and therefore the workload has to be tailored to be able to see that. So the idea is that we're on the workload, then we look in memory and we see for the data we have queried or modified, and if we find that if it lights up in RAM, then we know this is the memory that corresponds to that operation. So in order to achieve that, you have to have workload that's specific to the operation that you're tracking. So for I/O buffer, we designed, or rather created 300,000 random select queries. I/O buffer caches data in memory. Therefore, you want to run a bunch of selects that read pages from disk. Now, it isn't completely trivial, because if you read too much, then the database will choose to not evict too much stuff from cache. So if you scan the whole table will not be placed in memory, because that means you have to kick out a huge amount of pages to make room. Therefore, there are rules and thresholds. You have to read some, but not too much, because if you read too much, it's not worth caching it. Therefore, there is a bunch of queries that read a small amount of data, so that it's actually cached and kept in memory. So that's the buffer area. For the sort or memory intensive area, we needed something that performs a memory intensive operation. So we have this big query that runs a join and an order by, which is a sort the data. Now, it doesn't stop there. If you simply run this query and then take the snapshot of memory and then of the memory process, then you will not see this data, because sort area belongs to the group of local allocated memory, meaning that it is released when the operation is done. So if I run the query, let the query finish or disconnect depending on the database, then the memory would be used for the query and then released back to the operating system. And therefore, when you grab the process of a database, it's no longer there. So for that workload, we had to capture the memory while the query is running, because by the time it's done, it'll be deallocated right away. And then for transaction buffer, we've designed a bunch of updates that will show up in that buffer. The only subtlety there is that only changes to the data will go into the transaction buffer. So selects will not appear there because they're not relevant to the question of recovery. Only when data is changing are you concerned that on crash you might lose a change. And the query buffer, which is the fourth one, was actually the simple one because more or less everything goes there. So we did not need a special workload for that one. But for everything else, the workload is tailored to exactly what it does. So now each one of those graphs represents the database. We've came up with our own term. This is not an industry standard, at least not yet. We call it spectroscopy after infrared spectroscopy, which is a chemistry operation that chemistry analysis that lets you see how much light has been absorbed. And Jay is having a lot of fun because he's a chemist in this group, and therefore that's where it came from. But you can see how much light is absorbed at different frequencies for a material, and we replicated the same thing for the process snapshot in memory. So what you see here is we've taken the process snapshot, which is the entire process contents of the database in RAM, and then we've broken it up into 200 points, so 0.5% buckets. And at each point, we've measured how much of our relevant data we have seen. So the x-axis is just the offset going from 0 to 100% within RAM of the entire process. And the y-axis is how full it is within 0 and 100%, although it's a very rough estimate because we have just estimated how much metadata there is. You don't expect data to be packed 100%, so we don't expect it to be 100% full. It's a rough estimate. It just gives you a sense of how much content there is. So this is the MySQL content of the memory. So all of the 4 memory areas are there. We looked for the specific data we accessed. So for I/O buffer cache, which is the biggest chunk over here, we have looked for the data we've selected, or the pages that we've accessed. For the sort area, we've looked for the sorted result of the query that we have executed, and so on. And this is one representative snapshot of several that we've created, but they were all pretty consistent, and you will see later you will see an example of what I mean of how consistent multiple executions, multiple new executions actually are. Now, the interesting part, and all of this, by the way, is configurable. So sort area and buffer cache, this is all something you configure, and it is consistent with what we configured it to be. So you decide how much buffer cache the database creates, and you can tune it. And that's one of the things that's useful to understand of how it's actually working. And all of those sizes were consistent with our settings that we've chosen. Now the interesting thing here, in a second you'll see that in other databases the I/O buffer cache is much smaller. It's not at 50%, but rather at about 20 or 30%. And there is a reason for that. So MySQL specifically uses index organized tables. Reminder, index organized tables are systems where you do not have a separate index, but rather you have one big structure that contains pieces of both the index and the table itself. Therefore, the buffer cache is primarily containing the data we've queried. In other databases, you see pages from the table and pages from the index. And we're only counting the actual data we look for. So in a system where you have a bunch of pages from an index, there's much less actual table data. But in this case, there is no separate index. There's only one structure, index organized table, that contains both. And therefore, this is much more densely packed with queried data, since there's much less metadata to surround it. So that's MySQL. Now for Oracle, and as you can see, the sizes were consistent with the settings, as I mentioned. It was the offsets are pretty consistent for a particular process, although that obviously varies by database. So where the buffer cache lives is more of a database choice. For Oracle, the fill of the memory is about 25%, and the reason is we actually have indexes, and indexes are also present in the buffer cache, and we don't count those because they're not part of the data itself. And then the query cache and the transaction buffer, there's not a lot of interesting things to say about it. They're consistent with settings and they're there, and you can find the data. The sort area is an interesting thing. There's a lot more about it that we can say. So in MySQL, the sort area is just one big spike. Again, we don't expect it to be 100% full because there's a lot of other stuff, and it's a very rough estimate of how full it is. But it is one big spike versus the sort area in Oracle that in fact contains a couple of different spikes and there's nothing in the middle. The reason is, in Oracle, the sort area would be used for multiple operations per session, yes? All right. The sort area would be allocated for a user session, meaning that when you connect, one sort area is allocated, and it's used for all memory-intensive operations, both sort and others. And in this particular case, and because Oracle is a relatively clever system, it's actually using a hash join for the query. So in addition to the order by which sorts the data, it also runs a hash join, which builds a hash table to join the data. Hash join is a memory-intensive operation, and we're only counting the ordered data and not the hash join results, and therefore some of the sort area can be seen used by other memory-intensive operations, where in MySQL it's per query, and therefore and MySQL is doing a nested loop join actually. And therefore there's only one memory-intensive operation that it has to worry about. And here there are several, and that's what you're seeing. So all of those choices end up impacting the performance and how the memory is actually used and what you find. So that's Oracle. And then Postgres but the buffer cache is maybe even a little bit less occupied than before. The sort area is much more occupied, a higher fill. And again, 50% is about as high as we expect given how we make this estimate. Once again, the way the sort area is set is very interesting and different from other databases. So where in Oracle you get one area allocated for the user connection, in MySQL you get one sort area allocated for each SQL query. In Postgres, you actually get a memory area allocated for each operation. meaning that if it were doing a hash join and a sort, which I think it does in fact here, each of those operations would get its own sort area that when the operation is done would be released back to the operating system. So this is much more densely packed and much more tightly grouped because every individual memory-intensive operation gets its own amount of memory. So the hash join would be happening somewhere next to it, but it wouldn't be overlapping because it's not shared. Each one is done per operation. And when the operation is done, once again, this goes back to the OS, and we saw it in the OS, except that it's scattered. Once it leaves the process, it's sort of scattered wherever it was an actual entire operating system memory. So this is the other thing you see, and from this graph. And the rest is pretty consistent. So that's Postgres, and then we also taken the same workload and made a clean setup, and ran the same workload and the same analysis using MySQL with transparent data encryption enabled, which it supports. And first of all, you can see the the grayed out curve is the curve you saw a couple slides ago for MySQL. So as you can tell, it's quite consistent, except for some variations in how the spiking goes. Not only the height and the amount of data, but also the offsets of where the different memory areas are located are very consistent, which tells us a couple of things. Most of all, it tells us that from memory analysis perspective, it makes absolutely no difference whether or not you choose to encrypt your data in a database. So transparent data encryption keeps disk contents encrypted by key, but when things are brought into memory, they are decrypted. And therefore, this is not simply data we found in memory. This is the readable content that we were able to match to the stuff we queried. Because when you actually access the data, you have to decrypt it. As far as RAM is concerned, it actually made absolutely no difference whether or not you enabled encryption at the disk level. And once again, the sort area is a particular caveat or danger, because while the I/O buffer is at least kept within the process, the sort area is done per operation, per query in MySQL. So when the query is done, then the sort area is released back to the OS and can be found there. Because once you deallocate the memory, that's it. It's out of your hands. Okay, so that brings us to a number of future work things that we hope to do with this. So again, this is all very preliminary work. We got a pretty good sense about where data goes in memory and how encryption, decryption plays into that. However, in general, there is just so much you can do with this that we see happening. First of all, just understanding what does a piece of data mean. So we've done some forensic analysis before that told us what the data is and how to interpret it. But the same record or the same page or the same piece of data might mean a different thing if it comes from a different location in memory. Moreover, not every memory area actually uses pages, even though most of them do. So just understanding what are the pieces and what do they mean, because you might find the same record in two places, but it serves a different function. One is a fetched data into your buffer, another one is a updated transaction that lives in a completely different area. And the other two big directions we see happening are monitoring the system for security breaches. So there are a couple of tools, Infosphere something and IBM Guardium, that monitor your database for unusual activity, meaning that you set it up and it looks at SQL queries and it basically is looking for an account having been compromised. So if an account starts issuing unusual SQL queries, you raise an alarm saying that this person changed their pattern of access and perhaps someone hacked their account and it's not actually them. While it has its uses, the problem is that you're monitoring the SQL queries. First of all, you have to be sure you see them. And secondly, a SQL query can be obfuscated. That might be difficult to tell what the query is actually doing. Just like with C, there is obfuscated SQL. I encourage you to take a look. They're quite fascinating. So the nice thing about our approach, even though it's a little bit more cost-intensive, is that you see exactly what the system is doing. Because no matter how much you obfuscate your operation, when it actually runs, it brings data into memory following certain rules that we've discussed. Therefore, I can tell if someone's accessing the data, if someone's sorting the data, if certain query accessed this or modified this content or not. And because I'm looking at memory, memory doesn't lie. You can definitely tell what the system is doing regardless of how it was done. And in general, if someone bypassed the monitoring system, you can't bypass loading data into memory. So that's one, and the other kind of obvious direction is just profiling query performance and understanding how the memory is used, which parts are overloaded, and whether or not your configuration is doing what you hoped it is doing is obviously a very useful thing to see and debug. And for that, I can just give a nice illustrative example of what happens with Postgres. It's an actual problem. So in Postgres, like in every other database, you can configure the memory-intensive area size. And it would stand to reason that more memory is good, right? So a lot of people trying to improve query performance would go in and up this amount. And it looks pretty small. So if it's like 64 kilobytes or something, people would go in and up it to a few megabytes. But the problem is that in this particular database, the memory is allocated per operation. So if your query has a sort, a hash join, and a group by, then each SQL query from every user may allocate several of those. So what actually happens by saying, give it a lot more data, the memory starts thrashing, because every query might create multiple and at least multiple of those chunks of memory. And therefore, increasing memory will often, past some point, lead to a horrible deterioration, because database keeps allocating way too many of them. So it is meant to be small because of how it is used, since you might create many of them for each query. Alternatively, in some other database, the memory-intensive area is set per session, and then giving more is possibly a good idea, depending on how many users you have. So even when it's the same type of resource, the way it's used ends up impacting the performance, and it may be quite difficult to see without essentially observing what does in fact happen when you run the query. And there's probably a lot more uses, but those are the two additional ones beyond encryption that we see right now, and we hope to come up with more. And maybe you have some questions or suggestions on what we could do with it. Questions?
Interesting work. So I have two questions. The first one, how did you collect data? Did you instrument the code of the database engine to do that?
No, so that's the beauty of this storage analysis approach, and kind of builds off some of the work we've done on forensics as well. You don't need to know anything about the code or the system. So you run the data, you take the snapshot of the process, so you collect the process snapshot from the operating system, and then you just looking at how the data was piped through the database. So we looked at the snapshot, and then we saw if you selected this data from a table, and we knew what condition we put on it. We looked for this data in memory, and when we found it, it was a match, because we knew that this query would retrieve this data. We just had to make sure it's cached. And same with order by. You select certain columns, and then you look for those columns in order, because they're being sorted. And when you see them, you know that's the impact. So as long as you design your workload where you know what the outcome should be, you can just find it in memory. That's why we were able to use so many databases. You would note, quite a few of them are not exactly open source. So for Oracle, for Postgres, you can actually instrument stuff, but for Oracle, good luck with that. But you don't need it. You can just look at storage. This is the best part of the analysis.
That's beautiful.
All right. So this is not my area. So, but I was wondering, what is the dependency on the operating system that you are using? So is it operating system independent?
That's an excellent point. And once again, storage, memory doesn't lie, storage doesn't lie. In fact, the analysis was done on both Windows and Linux. Most of it because of the setup of convenience of setup. But we expect it to be completely consistent. Again, we haven't tested that extensively, but we've done a bunch of forensic work. It turns out that if you have a format, if a database has a format in which things are stored, there is really very little reason to change it at the data storage level for an operating system, because once you get to the byte level, it's basically the same. So it's completely independent. And in fact, the results are done both in Linux and Windows, mostly because I don't even think that Microsoft SQL Server has gotten to Linux yet, but some of them are easier to set up in some environments. Did you have a
Oh,
second
yes, I
one?
have
Yeah.
a second question. So, when do you take the snapshot?
That's also a good question. So it depends on what you're hunting for. For I/O buffer, you can take a snapshot more or less any time. In fact, you can run queries and just take it afterwards, right? So the buffer is just this global. So for global memory, let me be more exact. Just for global memory, you run whatever queries you need to create the effects that you want, and then you just take a snapshot whenever. Same goes for logs, for anything that's global. For local memory, which is typically the sorting, join, intensive operation things, you have to take the snapshot while the query is running. And I think in practice, Jay ended up taking a couple of snapshots because while it's running is not perfectly defined. So you take like a few apart. But the point is that you must take it before the query finishes, or whatever is the unit of operation, because memory is local. And when it's done, it'll just deallocate. And once it's deallocated, it's still in RAM, in fact. So you can still see it in RAM, but it gets scattered. In order to get it as a continuous and consistent piece, you have to take a snapshot of a process. It's still there, but it sort of just floats about. So you have to take, while the operation is running, and that's a little bit of a fine art of timing it. But that's kind of the point of local memory, is once it's done, it just gets thrown away and therefore leaked. So ultimately, and that's the go-to example, is that it turns out that running an order by query, adding a sorting operation to your query, essentially makes your data that much more vulnerable, because if you simply do a select, it's not going to touch any local memory, so nothing's going to leak. If you add an order by, you're pretty much guaranteeing that a bunch of that memory is going to be, allocated in this temporary area and then thrown back to OS. So, until a better system or modification to a database is available, avoid sort by and hash joins. Yes.
So you look at the different areas of RAM using any kind of processes, right?
So mostly this is the snapshot of the database process, which is a subset of the entire memory. So the areas of RAM are within the database process that we've identified. So the 0 to 100 graph that you see is all, it's not the OS, it is the, in this case, Postgres only, which is however much memory you've given or how much memory the Postgres process is taking up overall. And within it, we found the specific pieces. There are other specialized ones, but we looked for our 4 areas.
So my question is, you can have access to this part of RAM from any kind of processes.
No, right. That's a very good point. So this is the memory belonging to Postgres in this case. Presumably, obviously root has access to everything. You don't normally, unless you have permissions, you do not have access to this memory. We had, sufficient permission. The part that's kind of, significant and more general purpose is that the moment the sorting operation is done, this goes back to RAM, and then that could just be allocated to whoever asks for memory, right? So you can't ask maybe for the whole thing, but you can say, malloc, and create a bunch of memory, and some deallocated memory will be given to you, and if you keep doing this, you're probably going to hit memory that's been released into the wild. That's the part you can get without special permissions, because stuff is leaking. Things within Postgres, like I/O buffer cache, it belongs to the Postgres process. You would have to have enough permissions to get to some other process's memory. Absolutely.
So if I'm a user that's using the same database, so 2 users in the same database, and the other one can access the the other users?
No. So first of all, I mean, the database might have access control. If you have access control, you can issue a query to access someone else's table. To get access to memory, it would have to be the operating system level user that has enough access. So from the database, as a database user, your access is defined in terms of what records, tables, and columns you can see. To take a snapshot, that's an operating system level operation. So you would have to do it from the OS. Like you can't do, in SQL, you cannot take a RAM snapshot. You would have to do an OS level snapshot. But for stuff that's been released, you could just keep allocating memory, and sooner or later you stumble on stuff that's been thrown away. Because once it's deallocated, no one scrubs it. But yeah, no, you wouldn't be able to get access to database memory from the database. Not typically. It's the operating system administrator we're probably looking at, or someone doing a lot of ballots.
One more question.
Yeah.
So suppose these database people are like wary of somebody sniffing these things, operations.
Yeah.
What can they build in some sort of deceiving mechanisms to throw off this operation?
Oh, that's an excellent question. So, with the exception of the new Intel SGX that are all just a lockdown processor, I don't see how you really would, right? So the problem is that you essentially are processing the data. So on disk it is stored, so you can read it and decrypt it. In memory it is actually being processed. So with the exception of some homomorphic encryption that lets you operate on encrypted data directly, that's something you can do, but within limit of what's supported. The problem is that like the data has to be there. I mean, you can create decoy areas maybe, but ultimately, and that's why what I was saying for security as well. If I look in memory and something has been accessed subject to certain rules, it has to be there. Like if it didn't make it there, then this data wasn't processed. So I don't really think there's much you can do, except for the Intel. Like if you just lock down the processor, where you literally can't run any code that hasn't been signed, but that's not so much deceiving as just like preventing you from even seeing memory. But beyond that, that's the fun part.
Okay. Thank you. Any more questions? All right. If there's no question,
No more is on.
Okay. All right. Then let's thank the speaker one more time. Pizza is here, by the way.
Nice.